Thank you very much. So let me tell you a story. For that story, we have to go back almost exactly 40 years in time. So we are now in March 1986. And we see a person standing here, and his name is Ray Cox. We are in Texas, in Tyler, Texas, in the USA. Ray is working on the oil fields in Texas, and he had cancer in his back. The tumor was removed, and now he's going to a radiation treatment in the hospital in Tyler. Actually, it's his 9th treatment, and he's quite happy because this day is intended to be the first day of his second life. The last time he goes to that treatment, and he's very happy because these guys in Tyler have the most modern machine with this new thing called software. So he's going there, and just as usual, he's laying down, and then everything is prepared. He's lying on the table, and then this machine starts this typical summing and buzzing, and he's dreaming of his new life. And when he's wandering along with his thoughts, then suddenly there's something he would later describe as being hit by a lightning bolt. The radiation doses was intended to be something like 200 rats, and it was something like 20 to 25,000 rats. So in a few months, Ray will die. Not because of cancer, because he was cured of cancer, but because of software. Ray was killed by software. And so actually he's one of the first persons, and that's one of the most prominent cases, and if you want to look that up, that's the Triarchic 25 case. A lot of people died because of software. And of course, the manufacturer said that's impossible. We've done all that testing. That's physically completely impossible. Nevertheless, a lot of people died, were injured. So what was software 40 years ago is AI now. And we're seeing similar problems. But what have we learned at that time? The first thing is, we could have said software is evil. We do not allow software for safety critical systems. But that's obviously not what we did. And that's good, because if you have a look back to the past 40 years, software has saved thousands, hundreds of thousands of lives. So it's not about prohibiting progress, but it's about enabling safe progress, progress that benefits the people and doesn't put them at risk. The second thing we learned, these companies disappeared from the market. No safety, no value. Even if you leave apart all the ethical issues, if you have no safety, there won't be a market. And safety is something you cannot retrofit afterwards. That's something you cannot do later. Either you do it right from the beginning, or you will lose the competition. Yeah? That's what we've learned. And the third thing we've learned, even though software was at that time a new technology, the safety engineering principles, they happen at the system level. They are still the same, so we have to adjust that, what quality for software means, what is a sufficient quality for software in a safety critical system. But talking about risks, new hazards, that's something where we could adapt the safety engineering processes. And that's the same now for AI. And that's actually what we've been working on for the last 8 years. We call it safe intelligence. And of course, you could now say we are trapped in the past, so we should look forward to all the tech companies, and it's about AI and all this new data. But the point is, these tech companies are calling us because of safety. The tech companies are now building up safety centers. They're trying to dominate the safety standards. They're hiring the best safety experts in the world because they know no safety, no value. It's not all about safety, but without safety, it's all nothing. Because if your product is not safe, the market will not accept it. independent of any regulation, the market will not accept the product. You could say this is different for LLMs, and talking about safe AI for LLM is something different, but it's not. But that's something I'm happy to discuss in the break. So for now, let's focus on what's today called physical AI. So AI embedded into cyber-physical systems, into cars, medical devices, and so on. And if you talk about safe physical AI, it's actually about safe cognitive systems. Because AI, safety is not an AI property, safety is a systems property. And when we talk about the cognitive systems, or being an institute for cognitive systems, it's always this combination. Of course, it's about AI. And of course, we put AI to the same level as a system because it's very important, particularly in Germany and Europe, that we stop thinking in terms of cars with software, but we have to think in terms of software with wheels. That's very important. That's a complete difference. So we have AI, but it's always part of a system in any case. And at least for the next 5 to 10 years, if you have a look at safety standards, it will simply be not allowed to have AI alone in a safety critical system. It must always be in an envelope of conventional software and systems. But then there's a third ingredient that's often forgotten, that's the human. Because these systems work together with the human. And that's something we used to have in the past, because if you get wrong information as a doctor and you do misdiagnose a patient and this leads to wrong treatment, then that's safety critical independently if that information came from AI or not. But the human is a part of the system, what we often call socio-technical system. So if you have all these elements, intelligence in a system together with the human and all that playing together, that's a cognitive system. So for this talk, how do we address that? That's something in German we call that real intelligence. It's just like dual, but with 3 elements. So it's a 3-layer intelligence in which we try to combine the best of different worlds. And for this talk, I've chosen one thing we are working on these days, which actually has its origin in the defense sector, but it also comes, you can also in emergency disaster management and in many areas. And there we see 3 layers of intelligence. So one is the functional intelligence. That's what we typically have today for autonomous systems, systems that take decisions on their own. The functionality is intelligent. But in fact, that's not enough. So we as humans are very good, not because we are only intelligent, but we are adaptive. And if you have just in mind like a disaster management system or like military systems, the problem why in embedded systems we decided to use AI is the open world problem. So we cannot predict what an autonomous car is going to see. Our world is infinite, so we cannot completely predict the system. And safety is always a property of the system in its context. And if you cannot predict the context, you have a problem. But now, developing a system that one size fits all, one solution that fits to all the possible environments, to all the contexts, doesn't work. And that's why we have to adapt to that context, just like we do it. So when I moved to Munich, I had to learn driving again. So if I drove, I come from a more rural area in the Palatinate area, and people are a little polite to each other also when driving. But if you use that politeness on the Mittlerer Ring in Munich, you have no chance. You will stand there until you're going to starve, no chance. So you have to adapt to this new driving situation. That's something which we call adaptive intelligence. That's at a different level. And then, of course, we have to play together with the human. The system will have its limits, and in many areas we will see that AI is not going to replace a human, but it will augment humans with additional capabilities so that we can increase the efficiency. So let's have a look at these things. don't forget, we are still in the area of systems, and AI is part of a system. And the first thing, if you want to get to safety and want to use that, because this is one of the key strengths we have in Germany and Europe, and yeah, so we can use that. But if you give students, for example, and that's, could also tell that from industry projects, but I don't get into trouble if I talk about the student experiment. If you give students the task, identify people moving in an area. Because for automation systems, for production systems, we want to get rid of light barriers. We want to detect where are the humans so that machines and robots and humans can work together much more efficiently. So light barriers are not good enough. So try to use a camera to detect a person. So what they do is download the model. Yeah, it's the same if you use the most current YOLO, it will be the very same thing. Yeah, then they will detect, oh, it's a black person in a dark corridor in front of a dark background. Somehow this doesn't work. So what's then the typical reaction? Okay, let's train it with data that contains more training material with similar situations with dark backgrounds, dark clothes, and stuff like that. And then they realize, okay, they will never get beyond the 90% barrier. The point is you can look at it from a systems perspective. So what is actually the task? And from a systems perspective, the first task is we have to detect that something is moving. To detect that something is moving and where it is moving, we don't need AI for that. And then we can look not at the complete scene, but we can look into the bounding box and try to identify, is it a person in that bounding box or is it a robot in that bounding box? Which is a much more simple problem to solve. So if you do that, what you then see is that this is a very differential thing. What students did, that's something like 5 minutes, just a differential, the difference of two images, of two frames. And based on that, of course, you have some artifacts here, but you can get rid of that quite easily. So, and then, you know, in that bounding box, you safely identify there is something moving. You safely know there is something moving. And then you can have a look at, is it really human? Or is it another robot, for example? So how can we use that? So that's something where we apply that together with our colleagues in Augsburg, the Institute IGCV, on their shop floor. So if persons are moving, so in the worst case, we always detect there is something moving, and then we can still shut down systems, have the robots slow down their speed. But as soon as we see it's a person, then we can say, okay, it's a person or it's a robot. That's something what we see, for example, here. You can also use things like redundancy, different perspectives, and stuff like that. But that's the same principle. We first detect the movements, which is a non-AI topic, and then we can have a look at what is in that bounding box. Is it a robot or is it a person? Yeah, and you can see our team is very motivated, doing some exercises during the experiments, and based on that, you get very safe systems. It's AI, it's very modern AI running there, but it comes from a systems perspective, and it's integrated in a conventional software engineering systems engineering task. And by doing so, you can use the potential of AI, and at the same time, you can guarantee safety, because we combine the properties of a system and of AI to get the best of both worlds. But that's only one thing. The next thing is adaptive intelligence. So who of you knows David Kahneman? Thinking fast, thinking slow? So a few. Okay. So let's do an experiment. So some people say, okay, that's not true. Our mind is much more complex and so on, but for imitating, it's, I guess, good enough. So you see now words, and your task is per word. If it's written in upper word, you say upper. If it's written in lowercase, you say lower. Read it word by word. If it's written in uppercase, say upper. If it's written in lowercase, say lower. Clear? Okay, you ready? So, if you're now a statistically well-distributed audience, at this third word, you hear a voice saying lower. That's your system 1. That's very autonomous, very fast. Yeah, it's the first voice you hear, but it's obviously wrong. Yeah, that's your system 1. That's something very fast, very autonomous, but unreliable. That sounds a little bit like machine learning. Then you hear a second voice. Hey, it's not your job to read. You have to look at uppercase, lowercase. So this is upper. Then the first voice is not yet convinced and comes back, no, this is lower, just read it. And then there's a short dialogue, and then at the end, your system 2 wins. System 2 is slower. It's at the symbolic level, at the semantic level. Yeah, it takes some time, but it monitors our system 1. And it takes over control in situations that are new to us. Yeah, that's system 1 and system 2. And that's exactly something that happened. This dialogue is in a fraction of a second. This happened for you now, but that's something we can imitate for technical systems. And as I said, one example where we can apply that is that we have to put AI into a safety envelope. We need to have a conventional supervisor, but these supervisors are typically too conservative. So they are safe, but they restrict AI so much that we don't have the benefits of AI. But what we can do now at this higher level is to adapt to a situation. Let's have this example from the automotive world. You see that, you cannot really see it on the picture, but in reality you would say, okay, this guy has the turning lights on, you know this car is going to turn right. So you know, okay, there's nothing, there's no pedestrian crossing, nothing, the road is free. When I'm at that position, this guy will be out of my way. So then you know, okay, this is the intent of this guy. Then you could say, okay, even if something strange happens, I could still pass by on the left. So no need to really keep the distance very long and stuff like that. So you reassess your risks, and you prefer smooth driving over maintaining a worst case safety distance to that car in front of us, which is quite intuitive for us. It's quite difficult. Of course, you could train that into AI, but once it's trained in AI, we cannot prove its safety. So, but we can bring it to the adaptive side. So conservative safety supervisors would be too conservative, and we start to mix comfort and safety. So we cannot brake too much because that's not comfortable for the user, for the passenger. So we combine these things. But the safety system is there to really intervene in the last possible moment. And then we split comfort and safety. And if we do that, and if you have the same thing, then we can reduce the distance from 24, what we assume in the worst case, to 9 meters in the real case. This means we win about 15 meters. 15 meters in our cycle times is a lot where we can decide what's going to happen. So we can have much more smooth driving. Typically, to do that, we need a lot of AI, and if you have AI, we cannot use it in the safety critical path. So that's a paradoxon we have to solve. So what we can do is we have this main function. This is in a context like our road. Then we have something like a safety player. That safety player is going to intervene if something goes wrong. So it's braking if you get too close to an obstacle. And then we have something what we call a counter player. And this counter player optimizes the main function. It adapts the main function and its functionality in such a way that it optimizes utility and minimizes the likelihood that the safety player is going to intervene. The safety player is still in place. This means the counter player is not in our safety critical path. So we can use all the fancy things for the counter player. And just play against the safety player. We do not want to bypass this, we do not want to cheat, but we want to optimize the behavior that it's the maximum utility without safety intervening. So if you have a look at that more closely without going too much into detail, so if you are in the field, there's something, for over 20 years there has been the community of self-adaptive systems. And if you do self-adaptive systems, we typically say we have a managed system, that's the main functionality, and we have a managing system, which considers the context and then adapts the main system to fit to that new context. And that's exactly where we can fit our system 2 into. So we need some models to have some formal representation of knowledge at runtime. So what is safe? What does safety mean? How does the context look like? We have a system that we can adapt. And then inside there's an analysis step where we try, okay, in this context, how do we need to adapt the system so that we get the highest utility without violating safety? So we have to interpret the situation to predict what's going to come and then do some exploration. And for that, we can use AI technologies. Typically, it's not the latest fancy technology. It can be very simple things like training Bayesian nets, can be fuzzy inference systems, can be support vector machines, something like that. But here we bring together AI systems together with self-adaptive systems, and based on that, we get our layer 2. So there's still one layer missing, and that's the cooperative intelligence. Given the time, I don't want to talk about that too much in detail. But of course, I just talked to the colleague at my table there. Of course, it's hardly anyone working in software engineering who's not looking at how to use AI in software engineering, and but how can we trust all that? And of course, that's also something we do. Safety engineering is a very complex task, and so we can close the circle. It's not only safety in spite of AI, but it's also safety because of AI. But there, of course, we need all these things. And that's an interesting example because if we do that and use AI, LLMs, and all these things for safety copilot, safety assistance, so how can we make sure that the results are still safe? That's also an ethical question. Could one AI say that another AI is safe? One AI says another AI will not hurt a person, or is it up to a human to prove that? But once we have these assistants, does the human really prove that? We have a lot of things like complacency. So we are not very good in checking things. That's also true for medical scenarios. So if you get a cancer diagnosis for the physician, it's almost the same effort to counter-check, to cross-check the result. It costs as much effort as just redoing the diagnosis him or herself. That's hardly a benefit there. And the problem is, at some point, we simply trust these things. If it works 10 times, we believe in the 11th time it also works. So we as humans are not good. But there's a lot of things going on where we simply do not exactly know what that means. And so what we are, for example, also working on is then the big question, how do we have to build the team between AI and the human in such a way that we can reduce the workload of the human, but nonetheless, we have the human still in the loop and activated that we make sure the human can really check the results. And for that, one thing we also do is we have some teams working on brain-computer interfaces, and we use this knowledge to really analyze the brains, because if you have surveys in experiments, of course, nobody would cross, no, I did not pay attention, I just clicked approve. Nobody will cross that in the survey. But in BCI and EEG, we see that. And based on that, we can see what type of interaction really keeps the user involved, what leads to complacency, what reduces complacency, and all these things. So that's still ongoing, but never underestimate the role of the human in such systems. So my counter here is running to the end, so let's come to the summary. And I want to make it very short. So I come from software engineering and from safety, of course, big fan of AI, but nevertheless, I know it's not all about safety, but without safety, it's all nothing. So we have artificial stupidity, and without safety, no value. The big techs know that. We have a lot of competence in safety, so let's use our competence as a competitive advantage instead of blaming it as stifling innovation. Thank you.
Okay, brilliant. I know it was a short time to discuss. Do we have any questions? So who wants to start with the first question? There are going to be 2, maybe 3 questions, so this is your unique chance to ask a question. So who wants to start, ladies and gentlemen? Perfect, so gentlemen at the back. Okay, let's get you the mic. Good morning, good morning, good morning. Hello. So here you go.
Thank you for the great presentation. My question is, you said the human in the loop is the critical thing to reflect on what these systems are suggesting. As a university professor, the question is, how should we train our students that they are capable of being this element in this system?
Yeah, that's an interesting question. We also have that, and there are 2 things. The one is human in the loop, so we really have to take an active role, and then there's something called human on the loop, where we mainly monitor things. And what I typically say is we have calculators. Nonetheless, we teach our students math. Yeah, so and what we get as a new task as universities is really to teach them really, the things lying behind that they can really plausibilize what the results are. And that's, I guess, something that, I don't know if you're aware of that. At TUM, we have these colleagues who invented this one tutor system, LLM-based, which does not provide answers, but it points you to different directions. Have a look at it from that perspective. Yeah, so there's still something missing. So it's teaching them to learn. And that's the same what we try to do for the safety system. So the safety assistants do not only give answers, but they have a tutor mode, training people, because one of the great risks we have is that if you have these systems for a few years in place, then we don't have experts anymore who are able to plausibilize it. Then really teaching them, looking behind, plausibilizing things, understanding what's going on. So that's just like we had it in the past. I always remember my math prof saying, okay, so you have to go through integration and analysis and all these things, even though the software can solve these things for you, because you cannot plausibilize the results if you don't understand what's going on. But that's something, fighting against this temptation of having solved everything by AI. That's, I guess, a didactical challenge we are facing right now.
Thank you for the answer. Thank you for the question. One more. Okay. The gentleman at the back was first, so please come closer a little bit. Thank you so much. Good morning.
Good morning. Really cool presentation. So from an intellectual perspective, I fully agree with all those cool systems, and then we draw our IT boxes with the architectures. But then, at least I have the experience that then sometimes US companies show up and they just throw a lot of data at it, like with LLMs or Tesla with self-driving cars, and all of a sudden, at least it feels like they are outperforming our fancy, explainable boxes, dedicated algorithms. So what would you say if some of our students or colleagues address me with these questions if I'm always supporting the fancy security boxes you were showing?
Thank you.
Yeah, the problem we have a little bit, it's manifold. So one thing is our human brain is not able to imagine the concept of nothing, of absence of something. But for safety, what you sell is the absence of unreasonable risk. That's something we cannot imagine. That's just, if I tell you do not think of pink elephants, so this doesn't work. And additionally, there's a cognitive bias in our brains. So systems hardly fail these days. So we believe it's not relevant. Yeah, that's the conclusion, but they do not fail because we've invested a lot of effort in them not to fail. On the other hand side, we are living in a world that's driven by permanent acceleration. There's the fear of standing still. So therefore, this fancy show of AI is always more compelling than the safety things. But the problem is there's an 80% illusion. You get easily to this 80%, but if it comes to human lives, and that's what we currently see in the US, Tesla paying $240 million for their co-pilot type of things. And that's exactly what typically helps for my students is if we are in contact with Waymo and all these companies, and then inviting them to the lectures. Because they do not only throw data at that, they have their safety teams doing exactly that. They are the unsung heroes. Because that doesn't fit to this big show story, but it's exactly that they have in the background. They have guys from avionics, they have guys from automotive, they have these old safety guys doing exactly that. And if they show the big show and bring their cars to London, it's not solved because they are throwing more and more data on that. It's solved because they have these safety guys in place. That's something you do not find in the headlines, but if you know these guys, and then if the students hear it from me, that's the same thing. Yeah, if the students hear it from the Waymo guys or from Amazon guys, NVIDIA is now driving our main safety standards. And if these guys come and say, okay, that's what you have to do. And there's so many people doing machine learning. The ones we're looking for can machine learning and safety, and they earn the money. And then you have them on your side.
Thank you so much for the answer. Thank you for the question. Ladies and gentlemen, one more round of applause for Professor Mario Trapp. Professor, thank you so much.